About to reach for a stick. Luke. All right, Luke. Following this okay so far? Little? Okay. I want you to tell me about what I should draw as a general picture. A sphere, right? So the way I draw spheres is I draw a circle, okay? And then I draw like this ellipse kind of in the middle, like this. Kind of a weird looking ellipse. That gives you kind of that sphere look. And anytime I draw spheres, I like to put a center and I like to throw a radius onto it just because, right? Now, this thing is changing, right? Growing and stuff, so I'm not going to touch this. So what about for the instant in time? Is there anything you can tell me about the sphere at the instant in time? Okay, it's increasing. Is there anything at that instant in time, what's fixed? The volume, good. And what is it?
36 pi.
Volume is 36 pi. Cubic feet, but that's not that important, all right? Okay, so here this thing is growing, right? At the instant in time, the volume is fixed at 36 pi. So that's like, take a picture. There it is. All right, I'm going to let you keep going because you seem to have this. What are we given? What is, and we're looking for, well, I'm just going to shut up. What are we given?
That constant rate.
Okay, the rate. This rate right here?
Yeah.
That's the rate of change in what?
The rate,
Read it.
radius.
Yes, radius. Does everyone see that? If the radius of the sphere is increasing at a constant rate, so that first line is telling you that that number is dr over dt, right? And we're using dt because it's feet per second again. And what number goes there? 2 feet per second. Keep going. I think you got this. What do we want? How fast the volume. So what am I going to write here? dV dt, right? Okay, at what particular moment in time do I want this?
When it's 36.
When what's 36? The what of the sphere?
Volume.
The volume. So I'm going to say here at the moment that the volume is 36 pi, right? Perfect. You did all of that, you did perfectly, right? Now what do you need?
How fast volume.
Well, yes, we need that, but I'm saying what's the next step then?
Find the equation.
Equation that relates what two variables together?
Well, radius.
Radius and volume of a sphere. So do you have somewhere available to you a formula that relates the volume of a sphere to its radius? And this is where you have to go maybe look up in a book, or maybe you know it. It depends on you. You don't know. Okay, so that's okay. So someone has already looked it up or had it memorized. What? Anyone have it? 4/3 pi r cubed. Now where'd you get that from?
The thingy that you told us to down.
That's your formula sheets, right? The formula sheets have formulas for spheres and cones and cylinders. All right, so that is something you would have to reference if you didn't know it. The reason why I'm so happy to see that formula is because it has v and little r in it. And so I know when I differentiate this with respect to time, I'm guaranteed to get a dr dt. I'm guaranteed to get a dv dt so long as I differentiate it correctly, right? I have to do the differentiation correctly. And I'm not going to do it, and we're going to let Luke off the hook here. It's going to be Danielle, but I don't think Danielle's here, no? Ronnie? All right. Let you catch up. You let me know when you're ready. Ronnie? It is Ronnie, right? Okay. Are you good?
Yeah, I was just trying to write it down before.
Yeah. Have I given you enough time to get it? Or were you writing the derivative down?
Yeah.
Okay. Well, we'll see. What's
That's
dV/dt? Okay. What part of this are you going to kind of ignore? What's a constant on the right side? 4/3 and pi. All that's a constant. Let's just bring it down, okay? Okay, Ronnie, then since you're just bringing that down, all you need to tell me is what the derivative of r cubed is with respect to little t. 3r squared, drum roll, dr dt, right? And what happens if you miss that dr dt, Ronnie? You're done, right? You're pretty much done at that point because then the thing you're trying to work with is not there, right? This dr dt that has a value of 2, you never account for it in there, right? Okay, and remember, I'll say it again, when we were at the equation, we never plugged anything in, did we? We waited till after the differentiation. All right, now we look at this. I like to look at this and just make sure I have everything here. dV dt is what I'm looking for. Happy to see it. 4/3 pi times 3, don't care about. R squared, do I know what the radius is at the moment in time? Ooh, wait a minute, hold on. Do I know the radius at the moment in time? No. I don't. I know the volume at the moment in time, don't I? And if I know the volume, can I get the radius? Yes. I can. So r is not explicitly given to us here. We're going to have to go figure out what r is. But we can, right? Because now I can fix everything. I can look at the instant in time now. And then dr dt is 2. So the only piece of this I don't know, the only piece I don't know right now is this, right? So I'll go get that over here now. And do it right here. So we need little r. Good job, Ronnie. Salo? Okay, help me get little r. We're allowed to look at this, right? We're allowed to look at this now. What we know is that the volume is 36 pi, right? So you can tell me that 36 pi is equal to 4/3 pi r cubed, right? And you can take this and solve that for r now, can't you?
Yeah.
Okay, so if I were to solve that for r, or if you were to solve that for r, what would you do? Okay, you just want to do like this, 4/3 pi, you just want me to do the whole thing on both sides?
Yeah.
Okay, that's gone there. Pi's are gone? What does that turn into, though?
108 divided by 4, 3r.
Yeah. Yeah, so this right here is 27. That should be 27. So you could do, just flip it, right? Just multiply by the reciprocal, 3/4. So multiply by 3, divide by 4, or divide by 4, multiply by 3. However you do it, I expect everyone here could do that. R cubed. And now you take the cube root on both sides, and the cube root of 27 is 3. Do I have to do plus or minus? No, not with cube roots. So r is 3 now. So if a sphere has a volume of 36 pi, then that means its radius had to have been 3. And now we can come back over here. Plug it all in. dV dt, which is what we're looking for, is equal to 4/3 pi times 3 times 3 squared times what? 2. So that's just plugging everything in. I think a lot of things start to clean up here. That's gone, that's gone. What's that? Is it 72? Is that what I heard?
I got 72 pi.
72 pi. 72 pi what? Volume over time. Volume is measured in cubic units. So what were we measuring here? Feet? So cubic feet per second. So if you have a sphere where its radius is growing at a constant rate of 2 feet per second, then the moment that the volume is 36 pi cubic feet, at that exact moment, the volume is increasing at 72 pi cubic feet per second. Do you all feel like you're catching on to this? Yes. Okay, good. We're just still kind of scratching the surface here, but we're getting there, all right? Go ahead and read that while I put our stuff here. And just so you know, in case you go to the tutoring lab or something like that and get help, I'm pretty sure they're not going to do this general instant given want equation thing, because it's not usually something you see like in a book or anything. I think I just did that when I was learning it. It just made the most sense to do it this way for myself. Do you all have enough time to read that? Okay, good. Lanissa. Yeah? Okay, so what am I going to draw? Sphere? Yeah? That's changing, right? Growing. All right. How about at the instant in time? Draw what? Sphere? Anything you can tell me about at the instant in time? Surface area is what? Is that the surface area? So you see this square feet per second? When you think about that, think about you driving down the road at 40 miles per hour. That's a speed, right? That's a rate, and that's a derivative. So this is part of a derivative. This number right here, the volume is 36 pi cubic feet, is talking about the volume of this thing at an instant. So how fast is the volume increasing when? So this is like, take the picture, at exactly the moment, the volume is 36 pi cubic feet. So here, volume instead of surface area. Understand that? Okay, 36 pi cubic feet. All right. Now, isn't that the same volume we had on the previous problem? It is. So we know what radius is going to be here because we already did this in the previous problem, right? The radius here is what? 3 feet. So we actually know a lot of information about what's happening at the instant in time. Do you want to keep going? Yes, of course you do. Okay, what are we given? So this is a derivative. You were on to this a second ago. So we're given what? The rate at which what's changing with respect to time? Area, right? So what should I write here? It's always going to be d something over d something. So what is it? dA over dt. Now, everyone please understand, we're going to use A for surface area. Still an area, right? And what did you say that was? 20 square feet per second. And what is it that we want? I'm going to let you off the hook here in just a second. What is it that we want? So somewhere in there it's going to say like how fast or something like that. Volume, right? How fast is the volume increasing? So we want to know d what? dV dt. And what do we want to know that at exactly the moment that what? When the volume is 36 pi. Okay, that all make a little more sense? Okay, next person on the blank. Wait. Daniela? Wait, Danielle. There's two. There's two. I think they're both. One's not here. Okay, David Garza. This going okay for you?
Yeah.
Okay, good. You get the equation. What are the two variables we have to relate together? Area, surface area of a sphere to the volume of a sphere, right? And I see you looking at that. What information did you have there? This is going to be scratch work on the side, okay? This is my scratch work. What do you have in terms of spheres? What do you have with area and volume?
Besides the previous equation,
What was the previous equation?
volume equals 4.3 pi radius.
Okay, we can't use that because this has volume and radius, right? We need volume and surface area. So you have another one there?
Yeah.
What is that?
Area equals 4 pi radius squared.
Okay, so here we've got two equations. One has V and R in it, the other one has A and R in it. So can we come up with a formula that has V and A in it? How? Solve one of these for R. Your choice. I don't care. Which one seems easier to solve for R? The bottom one, right? Let's take this one and solve it for R. So if I divide both sides by 4 pi, I get this. And then I have to take the square root on both sides. And when I take the square root, I should do plus or minus. But I'm not going to do minus because we're talking about the radius of a sphere, and that can't be negative. So I'm just going to have square root of A over 4 pi is equal to R. Yes?
Square root? Why square root?
Because I'm trying to solve for R. The problem is this. This volume formula has V in it but not R. This one has A in it. Sorry,
I couldn't make it out.
I said that wrong. This formula has V in it but not A. This one has A in it but not V. I need an equation that relates A and V together, so I'm going to have to come up with one on my own. I'm going to have to generate it myself. So what I do is I'm taking this equation, solving it for R, and then once I get this for R, I take that and do what with it? Plug it back into this one. So let's do that. If I take that one here, the volume will be 4/3 pi, and then R is actually this, square root of A over 4 pi, but then all of that, what? Cubed. Yes?
Would why can't we do like volume equals 4/3 pi r cubed, like take the derivative of that and then plug in the radius 3 feet?
That is an excellent question. And I'm going to answer it. So here's the question. The question was, I'm going to erase this because I don't think we need it. You said, why not take like this one and take the derivative of it with respect to time? I get dv dt equals 4/3 pi as a constant comes for the ride, then 3r squared, then dr dt. Right? Okay. And what do you want me to do with this? I mean, what's wrong with this right now? Why can't I use this?
Because we don't have derivative.
We don't have drdt, and we'll never have drdt. Well, we could get it actually, but we need to know what dA dt is first. So if you try and use this formula right here, you're going to run into some trouble, right? Now, there's a sneaky way to go about it. What was the area formula? 4 pi r squared? Now this is tricky, don't do this though. If I take derivative of that with respect to time, I get 4 pi as a constant. What's the derivative of this? 2r dr dt. Now, what I could do is I could solve this for dr dt and plug it in right there for dr dt, and then it would work. But we're doing that kind of anyway right now, okay? Can I move on?
Yes, sir.
Okay,
Thank you.
good question. We don't want to be taking derivatives of equations that have variables that we don't know anything about. We don't want to have an r in there because we don't know anything about dr dt. Okay, so here's here's where we are, right? This is a new equation. It actually relates V and A together, right? So I'm going to rewrite it one more time. Okay, watch what I do here. This is going to be A to the 3 halves over 4 pi to the 3 halves. Let's see if that makes sense. What did I do there? Yeah, square root on top and bottom, and then when you take a square root and cube it, you get 3 halves, 3 halves. All I'm trying to do right now is clean things up. On this bottom one, I'm going to leave the A to the 3 halves up there. On the bottom one, I can do this power on both of these, right? So what is 4 raised to the 3 halves? So you're supposed to take the square root of 4 and then cube it. 8, so you get 8 there. And then we have pi to the 3 halves. I can't do anything to that. Yeah, so but we do have pi to the first power here. And pi to the first power over pi to the 3 halves, you can subtract. And you get pi to the negative 1/2, and you put it back on the bottom. It's square root of pi. And then I can also do that and that. All I'm trying to do is get this like in the cleanest form I possibly can before I take a derivative. Pardon? I did 4 raised to the 3 halves. So 4 to the 3 halves is the same thing as the square root of 4 cubed. All right. I think I'm ready to write my formula down here. Volume will equal, what do we have? This was a 1, this is a 3, right? The pi over that. So we have square root of pi on the bottom. So how about I write it this way? 1 over 3 root pi. I'm pretty sure that's what we have left. Oh, that was a 2 down there. Yeah, sorry. 3 times 2, 6. Okay, everyone see that? 8, 4, reduce that. You get a 2 here. The pi over pi to 3 halves becomes a square root of pi on the bottom. 3 times 2 is 6. And we still have a to the 3 halves, right? And I'm going to leave it as a to the 3 halves because I'm about to take derivative of it. Questions? Okay, derivative time. Or should I plug in 36 pi for volume? No, don't do that. Yusuf? You ready? Derivative of this with respect to time. dv dt equals, what about that 1 over 6 root pi? That's all of what? So it's just going to come along, right? All right. Derivative of this with respect to time. 3 over 2, right? So 3 halves comes out. I'm going to have to erase this. 3 over 2 comes out. A, right? To what power? A half, right? Because you're subtracting 1 from this. Drum roll. dA dt. There it is. So let's just run through quickly and see if we have everything. This we're happy to see. That's what we're trying to solve for. Constant, constant, constant. Okay, do we know? Uh-oh, shit. Okay. dA dt I'm happy to see because that's what oh wait, I said that. Did I say that backwards? Yeah. No, I did not. That we have, right? That we're given, that's a 20. That we're looking for. A we don't have, right? But now I can fix everything. And if I know what the volume is, and I know what the radius is at the particular moment in time, then I can figure out the area. I just have to use that formula. Area was 4 pi r squared. And I know that the radius is 3. So the area at the specific moment in time is 4 pi times 3 squared is 9. So this is 36 pi. Huh. The area is the same as the volume? Right? The area is the same as the volume. Well, they're different units, though. This is cubic feet. and the area is measured in square feet. So it's just coincidentally, at this particular moment in time, the volume and the area have the same numerical value. Coincidence. So now you can plug everything in, right? Replace that with 36 pi, replace that with 20. That's dV dt. I'm going to stop there. I think at that point we can be done. We're going to do that one next time. We're going to do this one today. I don't normally get to this problem on the first day, but I'd like to today. I'll give you a moment to read this one. We got about 12, 13 more minutes, so let's 14 more minutes. Seven feet per second seems like a pretty brisk walk, doesn't it? Or no? 7 feet per second? That's moving pretty quick. All right, this is completely different than anything we've done, right? This is very different. No spheres, circles. This is different. What's that? Cylinder. Street light, yeah. We could draw, well, you could draw a cylinder for the street light, but what are we trying to figure out? Let's start with what we're trying to figure out, like how fast his shadow's moving, right? How fast his shadow's moving. So before I do given, instant, all that stuff, let me just try and understand, like do a quick sketch of what's happening. I've got the ground, right? I've got a pole. I'm not going to get as fancy. There it is. And it has a light on it, right? That light, we're assuming, is shining in every direction, like that. That pole is 20 feet tall, right? That does not change. It's fixed, no matter what. 20-foot pole. And then I have a man who's walking away from the pole. The man is 6 foot tall. That shouldn't change either, right? So here's my man. Impressive. 6 foot. Close enough. He's walking away from the pole. Now, can you visualize what his shadow looks like? So the light's shining, right? And like if you imagine connecting straight to his head down there like that, right? Then any light rays that go on this side, right, are going to be blocked by him. So it's going to cast his shadow on the ground. So his shadow is going to look something like this. Right? That's his shadow on the ground. It's impressive, I understand. This is years of experience, as you can tell. Right? I mean, a lot of people can do stickmen. Not many people can do stickmen shadows. Right? It's a whole different level. So as he moves, what happens to his shadow? So let's draw like him a little further down the way, all right? Let's see, a little further down the way. All I'm doing right now is brainstorming. I'm just trying to figure out what's happening, right? And then I'll try and figure out if I can answer the question. Now, right? Now his shadow has grown, hasn't it? Again, don't be jealous. Okay, no room for that. No room for that in here. I'm not quite sure why it got wider, but it did get taller, like longer. Okay, so he's moving, right, at a constant rate, and his shadow is moving. Street light is mounted 20-foot pole, 6-foot man walks away at a constant speed. So this right here is a speed, right? This is a rate of change. So you see how I drew this arrow here? I'm just going to put here like 7 feet per second because it's like how fast he's moving, right? It's just for reference for my own sake. How fast is his shadow moving along the ground relative to the pole when he is 12 foot from the pole? So what we're saying is this. At this instant in time, right, his shadow, we're going to talk about the tip of his shadow, so like the head. That right there, the distance from here to here, right? As he moves, that tip of the shadow moves. And so the speed at which the tip of the shadow is moving, right, it has a speed, doesn't it? The shadow has a speed. And what we want to know is how fast his shadow is moving along the ground when he's 12 foot from the pole. Kind of makes sense? So I'm going to try and draw a general picture. Pardon? General. I don't know why that marker looks so faint. I'm going to do a general there, and then I'll do an instant over here. Or I'll do it the other way. General here, and then instant. I'll give myself a little more room for this one. Okay, in my general picture, I have a pole with a light. I have a man that's 6 foot tall. And I have a shadow that hits at that point. Okay, so I'm simplifying my picture. Pole, man, shadow, tip of the shadow, yes? Okay, in the general picture, does the pole's length change? No. Does the man's height change? Okay. Does the distance from him, from the pole to the tip of the shadow change? Yes. Let's call this S for shadow. That okay? You call it X, Y, W, whatever you want. S is what I heard. Is that what y'all want? X? Y'all want to do X? Let's do X because it is horizontal and we've used X for horizontal our whole lives. So everyone understands that X is the distance from the pole to the tip of his shadow. Okay? With me? That's the general picture. That's it right there. This doesn't change, that doesn't change, but as this moves, X changes, yes? All right. What about the instant in time? (26). This time, what's fixed here? At the snapshot in time. The distance between the man and the pole is what? 12. So this distance from here to here is 12 at the instant we're talking about, right? I should also mention that when you do this whole thing with the general, the instant, the given, what you want, and the equation, when you do all this, you don't necessarily have to follow the sequential order, okay? I would wait for the equation till the end. But like you can start putting down what you're given and what you want and kind of go back and forth between these, put it all together. Can anyone tell me something about what we're given? It needs to be a d something, d something. dx dt is what? 7? What do y'all think? Think carefully about this. Is dx dt 7 feet per second? X is the distance between what? The pole and the shadow. So is the shadow moving at 7 feet per second? No, the man is moving at 7 feet per second, right? And I have not labeled that variable on this picture. I've labeled from here to here, right? The speed at which the man moves is not necessarily the same as the speed of the shadow. So I need to label this distance from here to here something other than x. M for man? Yeah, M for man. Now, what is this? dm dt, right? dm dt is 7 feet per second. All right. What is it that we want? dx dt. That's the thing we wanted. We want to know how fast his shadow is moving relative to the pole at what moment in time? When are we snapping the picture? When m is 12. Right? At this point right here, this is m. I have a question for you before we go answer this, because we only have like 3 or 4 minutes. Do y'all think that as he walks, his shadow, the speed of his shadow is speeding up or slowing down or staying the same? Y'all think it's speeding up? So as he walks, his shadow is getting longer and longer and longer. You think that that shadow is speeding up as he walks? We're about to find out. We're about to find out exactly what's happening in that shadow. Okay? Now, we need an equation. I'm going to run out of time. We need an equation, right? I think we have almost everything we are looking for. I need an equation that relates x and m, and we are going to pick on somebody here that's blank. Marcus? Anyone here? This is not, unless you have it, Marcus. Not sure? What do you got? Pythagorean? Close. Pythagorean with what triangle? You need to relate this variable to this variable.
You couldn't do proportionality.
Exactly. That's exactly what we need to do. We need to see here similar triangles. Okay, so this now we're going back. Okay, we're going back to geometry that you may or may not have in that brain of yours. There is so I need some scratch work. We have this thing that says this. If we have a triangle, a right triangle, and inset into it is another right triangle, then what you have are 2 triangles, small one, big one, right? They both have the same 90-degree angle. They both share this angle, right? Which means that these angles have to be the same, right? So this angle here and these two have to be the same. If this is true, then these 2 triangles are what are called similar, which means that the ratio of corresponding sides must be congruent, which just means that if you take the hypotenuse divided by the hypotenuse, it'll be the same as this side divided by this side. Or if you take the hypotenuse over this side, it should be equal to the hypotenuse of this one over this side. You can set up the ratios however you want. So let's take a look and see what kind of triangle we have. And we can't look here. We have to look here. We have a small triangle and a big one. Here's the big one. Here's the small one. Right angle, right angle. They both have the same angles here, same angles here. So they're similar. What can you tell me about that side? 20. What can you tell me about this side? 6. What's this distance from here to here? X. What's this distance from here to here? Ooh, yeah, it's this, right? It's not this, it's this. So it's not m and it's not x, it's x take away m. Right? Yeah. So now what I said is that the ratio of corresponding sides must be congruent. So you can set this equation up however you want. I'm just going to choose, all right? So here's my equation. I'm choosing to take this side, and I'm going to divide it by that side. So x over 20 must be equal to, what do I do on the other one? X minus m over 6. Okay, do we have an equation that has both x and m in it? Yes. So I'll be able to differentiate that, and we can pick that up at the beginning of class next time. No. Sorry, as you pack up, I just cleared fractions here and got my x's on one side and m's on the other. And right here at this point, I would take the derivative. What's the derivative of the left side? 10/7 dm dx, or dt, sorry, equals derivative of this side, dx dt. Do we know dm dt?
Yes.
dm dt is 7, and dx dt is what we want, right? So what is it? 10? 10 what? dx dt is 10 feet per second. Okay, now here's I know we're ready over time. What did we not use in this, when we got to this point, what did we not use? What was irrelevant in this equation? The m, right? How far he was away from the pole was irrelevant. Look at the equation. Is m in here? No, right? That means dx dt, the rate at which his shadow moves, only depends on dm dt, which is the rate that he's moving, which is fixed. Which means what? The shadow's motion, the speed of the shadow is constant. It is not speeding up as he walks. He walks at 7 feet per second. His shadow's moving at 10 feet per second, no matter where he is. So even though logically you may think that because his shadow's getting longer, it's growing faster and speeding up, it's not. It's just moving at 10 feet per second the whole time. As this illustration shows here. That's basically him walking away. So the rate at which the green is growing here is constant. Okay, go. Have a good day. I'll see you all on Thursday. You can start your homework for this section. I encourage you to do that. Don't erase? Okay. If you need to get any of that, just look at the video also, because that should be on there.